In this video we will discuss the verilog code of encoder, decoder, multiplexer and demultiplexer. Now here is a 4 to 2 encoder. Here first of all we simply define the module encoder, and here variable names A0, A1, A0, A0 and A1 are the outputs, while Y0, Y1, Y2 and Y3 are the outputs here. And we assign that y plus y2 is equal to a1 and a0 is equal to y plus not of a and y1. As we can see the circuit diagram of this by locating the RTL view from here. Here is the RTL view of the encoder circuit. Now we go to the university program VWF here. Here we insert the node finder here, list it, copy this and OK. Here we can see that A1 and A0 are the output and these are the four inputs. We set the inputs. Y0 is equal to 1 and Y2 is equal to 1. Now we simulate this. It takes some time to compile. We can see from here it shows the result A1 is equal to 1 and A0 is equal to 0, because from the coding A1 is equal to Y3 plus Y2, and from this Y3 plus Y2 is equal to 0 plus 1 is equal to 1, A1 is equal to 1 and A0 is equal to not of 1, not of A and Y3 multiplied by Y1, which is equal to 0. That's all for this, and now we'll move to the next. Here is a 2 to 4 decoder circuit. Here you define the variable input output, and here is assign the logical equations, not of A and not of B and enable. In all the case enable are the 1. If the enable is equal to 0, then no output is shown. Now we'll get the RTL view from here. Now here is the RTL view of the decoder circuit. Now we look at the RTL view of this. We go to the here uniform university program VWF, and here we insert the node bus, node finder here, list it, copy and OK. We set the input value A, B and enable is always 1. We set A is equal to 1 and B is equal to 0. Now we run the simulation here. It takes some time to compile. Now we can see from here the output at Y2 is equal to 1 and Y0, Y1, all the output is shown at Y2. Now we go to the next. Move next from the here is a 1 to 4 MUX, which is similar to the 1 to 4 DEMUX, which is similar to the encoder. Similarly, here is a it directly verify output and inputs are declared, and using the behavior modeling and case study we define the 4 cases and the output here, and here we end the case. Now we locate the RTL view. Here we go to the locate RTL view here. Now we can see that here is the RTL view of DEMUX. Now we go to the university program VWF. Here we go to the university program VWF. Okay. Here we insert the node bus here. Find node, copy, list this, copy this, and okay. Here A is A and D in are the outputs, inputs. We set the D in is equal to 1 and A is equal to 0, 1 here. Now we run the simulation here. It takes some time to compile. Here it shows the output. We can see that here it shows the output at Y3. Here we can see that here it shows the output at Y1 and Y2 and Y3 are the unknown, and Y0 is 0. Now we move to the next here. Here is a 4 to 1 MUX circuit, which is the opposite to the DEMUX and similar to the here we write a behavioral modeling of this circuit. Now we locate the RTL view of this. We go to the locate RTL view from here. Now here is RTL view of the MUX circuit. Now we go to the university program VWF from here. Okay. Here we insert the node finder here, list this and copy this, and okay. Here similarly ABCD are the inputs, S0 and S1 are the selector pins, and here is the output. Now we set the here S1 is equal to 1 and here we set 1 0 and 1 0. We set this 0 and this B is equal to 1 and all the other are the 0 0. Now we run the simulation here. Save this. It takes some time to compile. Now here we can see that here is the output shown. When input is at B, it shows the output 1 and selector pins are 0 1 statement. Now that's all for this.